All right, let's jump right in. Welcome to today's Explainer. So today, we're cracking open a really fascinating chapter from grade 8 math. It's simply titled Algebra Play. Now look, if the word algebra instantly makes you think of dry textbook equations, just endless strings of letters on a chalkboard, I want you to completely erase that image from your mind right now. Seriously, scratch it. Because today, we're looking at algebra as something totally different. We're going to see it as a secret code, like a hidden language that literally lets us perform magic tricks, unlock visual puzzles, and even predict the future. It's way more than just finding x. It's about uncovering the invisible logic that holds numbers together. So buckle up, because we're going to have some fun with this.
To kick things off, I actually want to prove to you that algebra is basically a superpower. So are you ready to play a little mind-reading game with me? I challenge you to actively play along right now. No calculators needed, just your brain, okay? I'm going to give you a quick sequence of instructions, and I want you to just do the mental math as we go. You ready? Let's do it.
All right, step 1. Think of a number. Literally any number at all. Just keep it right there in your head. Okay, step 2. I want you to double that number. Got it? Step 3. Add 4 to your new total. I'll give you a second to get that right. Okay, step 4. Now take that current number and divide the whole thing by 2. And finally, step 5. This is the last one. I want you to subtract the very first original number you thought of from the number you're holding right now. You got your final answer locked in?
I predict that the number you're holding in your head right now is 2. Am I right? I bet I am. And here's the crazy part. It absolutely does not matter if you started with the number 5 or 100 or even -37. Pretty much everyone watching this explainer just ended up with the exact same result, 2. But why? I mean, are we really doing magic here? No way. We're doing algebra.
Let's completely unmask this trick. If we look at the instructions on the left side, right side by side with the algebra on the right, the whole shebang just makes perfect sense. See, when I said think of a number, well, algebra just calls that unknown number x. Then double it becomes 2x. Add 4 gives us 2x plus 4. Then divide by 2 cuts both parts in half, right? So that leaves us with x plus 2. And then, here's the magic moment. Subtract the original number. We take our x plus 2 and we subtract x. That starting number perfectly cancels itself out. X minus x is 0. So all that's left behind is the 2. Honestly, this brilliantly illustrates how algebra lets us see the hidden machinery behind the trick. Like, no matter what starting number you throw into the machine, it's rigged to always spit out a 2.
There's this wonderful little comic from the source material that perfectly captures this. It shows friends just hanging out, challenging each other with these exact types of puzzles. And it's a great reminder that algebra isn't just some solo activity meant for, passing tests. It's actually a social tool. It's a way to investigate puzzles, model different scenarios, and ultimately totally entertain your friends by seeming like a mathematical mind reader. And the best part? Once you know the algebra, you can literally invent your own tricks to make the final answer 3 or 5 or whatever you want.
Moving right along, Section 1, Cracking Number Pyramids.
So, the rule of a number pyramid is super simple. The value of any block is just the sum of the 2 blocks directly beneath it. Imagine a pyramid where the top block is the number 60. Right beneath it are 2 unknown blocks, and we'll just label them A and B. Because of the fundamental rule of our pyramid, we know for sure that A plus B equals 60. But, well, that's really not enough information to solve the puzzle yet, is it? We need to dig a little deeper into the foundation of the pyramid.
Let's look at the next step and see how this builds. In our puzzle, the bottom row, the actual base of the pyramid, is made of 3 blocks, 12, an unknown C, and 8. Because the blocks above are the sum of the blocks below, we absolutely know that block A has to be equal to 12 plus C, and block B must be equal to C plus 8. So what do? We take our original equation at the top, A plus B equals 60, and we just substitute those expressions right in. That gives us 12 plus C plus 8 equals 60. And look at what we just did there. We took this multi-level, kind of messy visual puzzle and flattened it down into a single, totally understandable line of algebra.
Now we just combine our like terms. We have 2 C's, so that makes 2C. And then we add our regular numbers. 12 plus 8 is 20. Suddenly, our big complex pyramid problem is just 20 plus 2C equals 60. Look how clean that is. It's organized, and best of all, it's highly solvable.
So here is the crucial point. If 20 plus 2C is 60, well, we just subtract 20 from both sides. That leaves us with 2C equals 40. Divide that by 2, and boom, we reveal that our secret base number C is exactly 20. And the absolute beauty of this is that once we find C, the entire pyramid unlocks instantly, like a domino effect. If C is 20, then A is 12 plus 20, which is 32, and B is 20 plus 8, which is 28. Let's just quick check our work. Does 32 plus 28 equal our top block of 60? It absolutely does. Algebra was literally the skeleton key here.
And what's really amazing is that this exact same logic scales up. The source text shows that if you have a 3-row pyramid with base numbers A, B, and C, the top block will always, and I mean always, be defined by the expression A plus 2B plus C. It's just a predictable pattern. The chapter even applies this logic to famous historical math patterns like the ancient Virahonka Fibonacci sequence, where numbers are the sum of the two preceding ones. Placing those numbers at the base of a pyramid creates these magnificent spiraling algebraic patterns all the way to the top. It's really cool.
All right, Section 2, Solving Algebra Grids. Moving to a totally different dimension of logic, have you ever just stared at a wall calendar and realized the numbers are hiding secrets? The text outlines this really neat trick called calendar magic. Basically, if you take a calendar and draw a box around literally any 2x2 grid of days, say the 12th, 13th, 19th, and 20th, and add those four numbers together, there is a distinct, totally predictable algebraic pattern to the result, and it's based purely on how calendars are structured in rows of 7. Once you set that top left number as x, the other numbers are simply x plus 1, x plus 7, and x plus 8. It's just another real-world trick instantly demystified by algebra.
This logic is then pushed even further into abstract algebra grids. Imagine a grid filled not with numbers but with shapes, squares, triangles, circles. The only real clue you get is the total sum at the very end of each row or column. But by treating each shape as an algebraic variable, like let's say a triangle is y and a square is z, you can easily build a system of equations to deduce the true identity of every single shape on the board. It literally turns math into a high-stakes detective game of deduction.
And finally, Section 3, Algebra's True Power. As we wrap up our journey through this chapter, we really have to look at the big picture here. I mean, we've done mind-reading tricks, we've climbed number pyramids, and we've decoded grids, but what is the actual point of all this play? Well, the text makes it perfectly clear. Algebra matters because it is the ultimate tool for modeling complex numerical scenarios. It really isn't just about getting an answer, it's about justifying and proving why that answer works, just like we proved why our mind-reading trick always ended in a 2. It takes messy, confusing situations and gives them a clear, logical structure. And because it has this unparalleled power to model reality, algebra occurs in almost every single area of math, science, engineering, you name it. It is, quite literally, the invisible scaffolding of the logical world. Which brings me to one final, totally tantalizing puzzle from the text to leave you with today. It's a scenario involving a boy named Kareem who makes a deal with a magical genie. The genie charges a certain cost per round for a magical game, and through its powers, the genie knows exactly how many coins Kareem has. So, the mathematical cliffhanger is this. Using algebra, how should the magical genie set the specific cost per round so that it mathematically guarantees it will win all of Kareem's coins? I'm not going to give you the answer. I want you to grab a pencil, set up your X's and Y's, and use your newly refreshed algebraic superpower to crack the case yourself. Thank you so much for joining me on this explainer, and keep playing with numbers.